Okay, let's dive into this. Welcome back to another explainer. Now, I'll humbly admit right up front, today's topic gets pretty deep into the weeds. If you're a developer who completely obsesses over programming language design and advanced type systems, you are in the exact right place. Today, we're dissecting the Merg-E domain-specific language, which is being built for the Innuendo Web 3.0 stack. Specifically, we're going to explore a really brilliant leap forward in compile-time type safety.
Right out of the gate, I want to set some expectations. Merg-E is very much an incubator project. As developers, we are currently in the trenches, actively building the v0.3 specification and its runtime. So you can really consider this explainer to be a developer-to-developer sneak peek under the hood. We're looking at an early teaser for some of the v0.4 features that are coming down the pipeline.
I want you to consider this architectural puzzle for a second. Merg-E is uniquely positioned as a Web 3.0 data flow and crypto DSL. So how on earth can one language safely handle exact cryptographic lattices on the one hand and inexact physical data flow on the other, and do the whole shebang with absolutely zero runtime overhead?
Section 1. A peek at v0.4.
Taking a quick detour from our active v0.3 builds, the v0.4 specification extends Merg's existing data flow approach in two really massive ways. First, it brings in numeric-only n-dimensional matrices strictly tailored for cryptography. And second, it introduces compile-time dimensional analysis for physical quantities.
Section 2. The exact versus inexact split.
Now, what's really interesting here is the core philosophical challenge. On the left side of things, cryptography requires exact type-based mathematics, right? It totally relies on precise types like massive integers and rationals. But on the right side, physics and data flow simulations are inherently inexact. They operate heavily on float-based representations. Merg-E has to safely unify these two fundamentally opposing worlds.
To actually pull this off, Merg-E strictly categorizes its 7 numeric type families. The 5 exact families, whole, int, cent, rational, and crat, are used predominantly within a cryptography context, using standalone tensors. Conversely, the 2 inexact families, float and complex, are strictly reserved for physics-related calculations as embedded quantity tensors. The key takeaway here is they're designed to serve their specific domain without ever bleeding into one another.
Section 3. Tensors compile time only.
So what's the actual mechanism managing these domains? Well, the absolutely crucial point is that in Merg-E, tensors and matrices are related but fundamentally distinct things. A tensor is a strictly compile-time rich typing mechanism. It has literally zero runtime footprint. The compiler uses these tensors to enforce strict type safety, and once those checks pass, poof, the tensor completely dissolves. It folds its data into highly optimized runtime scalars, vectors, and n-dimensional matrices with absolutely zero overhead.
Let's deconstruct the syntax for a second. When you write a tensor in Merg-E, the compiler looks at 4 parts. First is the atomic type, the numeric foundation like a float 256. Second is the rank, 0 for a scalar, 1 for a vector, 2 for a two-dimensional matrix. You get the idea. Third is the shape, such as a 3x3 grid. And finally, the symmetries specification. The compiler uses these 4 pieces of metadata to strictly enforce type safety before erasing them completely, allowing your runtime to just fly.
Section 4. Safe physical quantities. Applying this compile-time logic to data flow, let me pose a scenario to you. In standard languages, a float is just a float, right? But in Merg-E, what do you think happens if you accidentally multiply an acceleration quantity by a time quantity?
Boom, you get a speed type. And this brilliantly illustrates the power of compile-time dimensionalysis. The system calculates dimensions exactly like physics. Length times length becomes area. But if you accidentally assign a distance to an acceleration or try to pass a dimensionless number like pi to a speed variable, Merg-E aggressively blocks it with a strict compile-time error. No runtime surprises.
And it goes even further. Merg-E enforces strict rules regarding the actual systems of physics being used. SI units like meters and seconds are kept completely and mutually exclusive from Planck units. See, in Merg-E, quantities are a safety feature, not a compatibility feature. Because the systems are mutually exclusive, there are absolutely no clever automatic conversions between SI and Planck units happening behind your back. If you try to mix them, the code simply will not compile. It's a purposefully dumb but incredibly safe design feature to guarantee the highest possible physical type safety.
Now, we all know that writing strictly within a single system's base units can get notationally painful pretty fast. So to alleviate that verbosity, v0.4 introduces the Thorn operator, a scaling literal operator. It's just a tasteful, pragmatic way to write cleaner numeric code, like quickly expressing kilometers, without sacrificing the ironclad safety of those underlying SI base units.
Section 5. Bringing it all together.
Ultimately, here is how the whole vision converges. Standalone exact tensors built on integers and embedded inexact tensors built on floats perfectly coexist. Whether you are defining a hyper-precise cryptographic lattice or a 3x3 physical stress tensor for a simulation, they both operate under the exact same zero-overhead umbrella. They are both entirely dissolved by the compiler before runtime even starts.
The language creator actually shared a really humble reflection on this design, saying, "It's all a bit verbose still, but the type safety this all brings should be worth the verbosity." And that's exactly it. It's a highly conscious trade-off. We are trading just a little more code writing up front to achieve absolute ironclad compile time safety across some radically different mathematical domains.
Which leaves us with this final thought. Knowing that Merg-E is actively building its version 0.3 foundation right now in the incubator, how will these zero-overhead version 0.4 type safety rules eventually reshape your next Web 3.0 architecture? Will you lean heavily into the precise crypto lattices, the inexact physical data flows, or a wild combination of both? Thanks for joining me on this explainer today. I really hope it sparked some massive ideas for your future builds.